All right. For this week, we will start focus on multiple linear regression. Yeah, let's start. Let's start with an example, a very simple example of multiple linear regression, which will have polynomial predictors. We also call it polynomial regression here. So, which, as I said, we model with a single predictor x and its polynomial powers like x squared and x cubic, etc. Okay, let's get to the example. And I think we talked about this salary data set before, where we collect information about how much the member make. And we will use polynomial regression to find the salary curve for a given profession. And this curve shows the normal salary of professionals with a given number of years of experience. So we have the salary value y and the years of experience being x, and we have a total of 143 data points. That's our sample size, and we want to find a 95% prediction interval for y when we're given x equal to 10. Okay, let's take a look at the data and the plot. So this plot is showing us our y value, the salary, versus our x value experience. So by just looking at the plot, it's definitely not a linear relationship, right? We see this curve here. It's more like a quadratic thing. But for illustration, we will start fitting a simple linear regression for comparison with polynomial regression. Okay, so this is what the linear regression looks like. This is our straight line. It does not fit well, apparently. And if we look at the residuals from the simple linear regression, it has a clearly very much a big pattern here, right? It's a curve. So this quadratic shape suggests that we should add a quadratic term to the model. So now we moved from a simple linear regression where we only have one predictor x. Now we would add another quadratic term, which is x squared, and take a look at the model first, where we have beta 0, beta 1 times x, and also this beta 2 times x squared. So this is the quadratic term that we added. And this is how you put it in R. When you fit the model, you have to put the letter I with this bracket, and then put your variable to the power of 2 to get this x squared into your model. And we plotted the line here, our polynomial regression line here as a purple line, and this one fits much better to the data. And a comparison of the standardized residual patterns, comparing this simple linear regression with our polynomial regression, it's obvious that the one on the right have no pattern, and it looks good. Okay, so yeah, that's a comparison of our simple linear regression and simple multiple linear regression model, which is a polynomial regression model. And I have a note on how to do the plotting. Like in here, how did you add the purple line to the plot? Because it's no longer a straight line. We cannot just use this AB line function to add the model to the plot. So a straightforward way is to plot the curve is to create a vector x. I call it experience new. It's a vector that spans the space you want the curve to be on. And then you do the prediction line. Prediction line, see this, I did the prediction, oh sorry, I did the prediction with your model, and you supply the new data as this vector of x cubed. So you supply this new data being this experience new, so your x value experience will equal to the vector that you just created. So this predict function gave you the corresponding values for y to the sequence of x here. And yeah, so these lines, you first supply the x value, which is this vector, and then is the y value, that's your predicted y value for this corresponding x. And then this is you specify the width of the line and the color. Okay, so this is just how do you do the plot? After you do the scatter plot, how do you add the regression line, this curve, onto your scatter plot? All right. Okay, so previously we have one predictor, but it's multiple term there because we have a polynomial term. And now we get to multiple linear regression with multiple predictors. So which is a like more generalized situation. So it's normally it's not enough to only include one predictor to make your model look good. So it's highly likely that we have to get multiple predictors, x1, x2, x3, into the model. So yeah, now I emphasize again, our y is called dependent variable and also called response. And all the x, we call it predictors, and we also call it independent variables. Don't get confused of what is y, what is x. So, well, for now, we are just working on the models, and for the next week, we will talk about the diagnostics. So just hold on that for 1 week. Okay, let's get to the model. It's very similar to the simple linear regression model, but we just have more than just this beta 1 times x1. So if you notice, we have multiple terms here up to beta p times xp. So in total, we have p plus 1 parameters in this model, plus 1 because we have this beta 0, beta now here. So what our model, the full model looks like is like this. So yi equal to beta 0 plus beta 1 times x1, beta 2 times x2, beta 3 times x3, etc., up to beta p times xp plus ei, which is, again, this ei is a random error. And the expectation of this ei when this x1 to xp are given is 0. So all the assumptions are the same as before. All the structures are the same, except that we have more than one predictors here, right? And again, if we want to estimate the parameters, beta 0, beta 1, up to beta p, we again use this least squares. Just again, it's very similar as before. You just got more terms here. We still get the residual sum of squares, RSS, and then we take derivatives with respect to each coefficient. So now we have t plus 1 coefficients, right? We have this b0 or beta 0 to beta p. So we have to do the coefficients derivative for each of them in order to get an estimate for them. And we solve the system equations to get our estimate for beta I hat, where I goes from 1 to p. So this is the background background theory. How do you get the coefficients estimates? And remember, we have also talked about how to get the estimates in matrix format. And in matrix format, now comparing this multiple linear regression with previously, the only change is this X matrix. So previously in simple linear regression, we have this column of 1 and 1 column for X, basically for X1. But now we have up to XP. And for each of these X, we have N observations, right? That's why you see this X1P up to XNP. So yeah, this is the difference comparing to before. And yeah, those are all the elements for this matrix format. Notice this X has changed to a much larger matrix. And again, the same as previously, we get the residual sum of square in matrix format. So this is the multivariate version of this summation thing. If you write it in this calculus format, it will be really messy. For the multivariate version of this calculus format, you will get a headache on that. So that's why people would prefer to use this matrix formation to derive the estimates for your coefficients. I have slightly a small note here about why we get this, but we have went over this. We have gone over this in week 2 when we talk about simple linear regressions. I'm not going to repeat this. This is just for your easy reference. I put it here in this multiple linear regression slides. Okay, and very similar, actually exact the same formula for your beta hat. Note that this X matrix has changed from previously. It's a much larger matrix now. So we still get our fitted values Y hat by plugging this estimated beta hat and get our residuals like this. So now, after the estimation, we get this Y equal to X times beta hat plus your error term. And we know the variance of this error is sigma squared times I, where this I is n by n identity matrix. So this is when you put it in the matrix format, how you denote the variance of this variance vector. Okay, so again, very much similar as before. We now discuss about the properties of the estimates you get. Basically, the estimate you get is an unbiased estimate because the expectation of your estimates, beta hat, will get back to the true counter value beta. So that's why we call it unbiased estimator. And similarly, if you get the variance of the beta hat, you get this sigma square times x prime s, the inverse of x prime s. And the unbiased estimator of the sigma square is this s squared, which is your residual sum square divided by the degree of freedom. This might remind you, like when we do the sample variance, like you might have wondered why you have this n-1 underneath in your formula. So this is basically the very general form. Like when you try to get an unbiased estimator, you use the residual sum square divided by its degree of freedom. So this is the estimator for sigma 3, which is this summation of all your EI hats squared divided by its degree of freedom. This EI is a vector of this EI, we write it as this. Okay, these are the series for your estimates. Well, we need all of this, like all of the background theory, because we need to do a test, or we need to testing on the coefficients if all the betas are 0 or not, and we want to get coefficients. We want to get the confidence intervals for the coefficients for those betas. So as you recall, if we want to do inference, we would have to get to the distribution of your errors, and or the distribution, basically the distribution of your estimates, so that we can do the test and confidence intervals. So now we have normal distributed error with constant variance. This is how we find the expectations of the beta hat and the variance of beta hat to prepare for the test and confidence intervals here. So we will use a t-test for the betas that we estimated. So this beta I hat minus beta I, which is the true value, divided by its standard error of your estimates, will follow a t-distribution with n minus p minus 1 degree of freedom. And the standard error of beta hat is the estimated standard deviation of beta hat. And we can, so that here I show you the formulations for that. The standard deviation, which is the square root of this, and we estimate the sigma square by this s square. And we can basically get that from R. And the degree of freedoms, I have a note here, is the sample size minus the number of parameters you estimated. So in this model, we have p plus 1 parameters. So beta 0 to beta p. So that's p plus 1 parameters. So that's why you see the degree of freedom being like this. Yeah, and this is all the theory behind the test and the confidence interval that we get from R. This is for your reference, basically. Well, we have an example here. We fit a multiple linear regression with, I think it's NYC restaurant data from, yeah, I think we have talked about this before. So, but in simple linear regression setting, now we are doing it with a multiple linear regression. Let's take a look at, oops, yeah, let's take a look at the code. All right. Let's see. Okay. So yeah, this is the R code I have for that example. Let's see. I first set up my working directory. So this is why I work in R. Working in R directory without like doing the R markdown. Like when you do R markdown, as as long as you put your data file in the same folder with your R markdown file, you do not need to like specify this setting work directory. But in R, like this plain, oops, sorry, this plain.r file, you well, convenient way to do this. You set working directory, which I already did, and with the data in, I read it already, and attach the file, attach the data file, so that you can refer to those variables directly. And I do a pair plot, like it's called a scatter matrix plot here. So well, maybe the better way is to take a look at the first couple lines of your data. So we have the price being our response variable. This is our y, and we have several several variables, other variables here. So I use this pairs function to get the scatter plot matrix, scatter plot matrices. Yeah. So on the diagonal, it shows all the variables that you have in this data set in YC. So we want to focus on this one and take a look at like the relationship of each of this variable, like each of this variable with the price variable. What's the relationship between our y with all other variables x. So for example, let's take one, like this one. For this small plot, the y-axis is the price, and the x-axis for this plot is food. So if you take, if you look at this, this row of the plot, it will give you like the one-on-one relationship between your y and each of these x. And for others, like if we pick this one, let's see this one. So if we pick this one, this is telling you the price versus decor, yeah, decoration, I guess, their relationship. Or like this two would be food versus decor. Okay, so this is just one way to visualize your data and find interesting pattern and to figure out maybe like what to include in your multiple linear regression model. So it's better to take a look at all of these scatter plot matrices. Oh, you might notice this east variable, it's strange, right? It's different from others because if you look at your data, this east variable is actually a binary variable. So it has only either 0 or 1 as the value for east. So it's when east equal to 1, that means it's in the east. When it's equal to 0 means it's on the west. Okay, so we have look at the data. Now let's do a multiple linear regression with our response variable being the price and our predictor variables, food, decor, service, east, and in the data set NYC. Let's do this model and we want to determine which of the three numerical variables has the largest impact. So let's do a summary of the this multiple linear regression model. So now, again, it's similar as before, but we have more than one predictors now, right? We have food, decor, service, east, and don't forget we also have this intercept. So determine which of the three numerical variables have the largest impact. Numerical variables, food, decor, and service. So food, decor, and service, basically, this one has the largest effect to the price, because like if you increase the decor by 1 unit, you will increase the price by 1.9. Yes. So is this one also the most statistically significant? Well, yes, right. By looking at the p-value here. So, well, yeah. So these questions are just where I copied from the slides. Like to make the most money, should the restaurant be east or west of Fifth Avenue? Well, look at this. The estimate for this east variable, which is a binary variable. So this estimate is basically telling you if you change from 0 to 1, which 0 means west and 1 means east. So if you change from west to east, the price or response variable will increase by 2.06. Right. So that means if you are on the east, you will have a higher, your price will increase. So it's better to have the restaurant on the east of the Fifth Avenue. Well, another question is, does it seem possible to achieve a price premium for setting a new standard for high quality service in Manhattan for Italian restaurants? Well, this is about the service. Let's take a look at the service estimates. Focus on this line. Oops. Yeah. So we notice this service is have negative coefficients estimate. Right. That means if you increase your service level, your price will not increase. Right, because it's a negative value. So for this one, the answer is no. And if you pay attention for this service, it has a fairly large p-value. So that means this parameter is not really significantly, is not very, is not statistically significant. Right. So we might consider not including this service in our model. Okay, so this is, we will talk about this kind of model variable selection or model comparison very soon. So yeah, this is just the example for multiple linear regression. And next, let's go to constants. Yes. Let's talk a bit about ANOVA. ANOVA is short for analysis of variance. So this is to test for a linear association between Y and the predictors. So if there is a linear relationship between Y and some or all of the X, we would have this formulation, and sum slash or of the beta I not equal to 0. So if y is only linearly related with x1 and xp, then all the beta 1, all the beta 2 up to beta p minus 1 will have to equal to 0, right? So the test, we're testing for the linear association, right? So the test, the hypothesis testing we're doing is that H now is that all the slopes, beta I from 0 to P. So all the slopes are 0 against the alternative hypothesis where it's at least one of the slope is not 0. So this is the alternative hypothesis. So this is what we are testing. So if at least one of the slope is not 0, that means it's not linearly related with all the xi's. Well, to do this ANOVA, we have to define a couple things before we can get to our testing. We can get our test statistic. Okay, the first one is total sum of squares. So it's the summation of yi minus y bar squared. It's also called SYY. You might remember this, the residual sum of squares. So that's yi minus y hat squared and sum them over all n observations. And we also have this regression sum of squares as regression. I think when we talk about the R squares, we have talked about this, right? And again, we know that the total sum of square is this regression sum square plus the residual sum square. And so which is basically the total sample variability equals the explained model variability plus the error variability, which this error variability RSS is not explained by the model. So if our alternative hypothesis is true, then the residual sum square should be small, right? And this regression, like SS reg, should be close to total sum of squares. Because remember, the alternative hypothesis is at least one of the slopes is not 0. So that's saying we have some of the predictors are correlated, linearly related with our response y. So if that's the case, then our regression should be close to the total variation. So the variability explained by our model should be close to the total sum of squares. And we use the test statistic F to do the test. So this F statistic is this SS reg divided by P, and this whole thing divided by the RSS divided by N minus P minus 1. And F is following, so this test statistic F is following F distribution with degree freedom P and degree freedom N minus P minus 1. So, and if our null hypothesis is true, so we have this distribution for this F. I think an easier way to remember this or to get an idea what is this doing is to look at this ANOVA table, where we have 3 sources of variations which is from the model regression and from the residual the error term and our total variation. And corresponding degree freedom for them are here, P n minus P minus 1. And this total is a summation of these two as well. So it's n minus 1. And correspondingly, we have the sum of squares, SS reg, residual sum of squares, and SST total. And what we used for this F statistic is basically the mean squares, where if you notice the numerator is this mean squares. So, well, the mean squares of this one is just the sum of square divided by its degree freedom. Similarly as here, and this F statistic is just this one divided by this one, right? Yeah, so we use this ANOVA table to get our F statistic. And remember, we talked about R square, which is the sum of square of regression divided by total sum of square. And that's the part explained by your model. Okay, and yeah, another note here. This is important. Yes. Well, R squared, the coefficients of determination of the regression line is the proportion of total sample variability in Y that is planned by your regression model. But this R squared is not really that robust when we try to use it, because if you add a completely irrelevant predictor to the model, this R squared would increase. So if we use this R squared to evaluate if our model is good or not, well, we can add more and more variables, more and more predictors to make this R squared large. So people have developed this adjusted R squared to overcome that non-robust property for the original R squared. So this adjusted R squared is defined by 1 minus this basically this is mean square error divided by this total sum square divided by its degree freedom. But if we go back here, the residual sum square, well, comparing to this one, let's do, so this R square originally is 1 minus this residual sum square divided by sum square total, where it have nothing to do with degree freedom, right? But in the adjusted R square, we have this RSS divided by its degree freedom, and also this total sum square divided by its degree freedom correspondingly, right? So in this way, we have this P here in this adjusted R square. So the number of predictors, so P is the number of predictors, right, would have an influence on this adjusted R square. So basically, if you increase the P value, well, it depends. If you increase the P value, it has some penalty on your R square adjusted. So we would use this adjusted R square to compare models when we have different number of predictors. Yeah. Okay, and so when we want to test for the linear association between Y and any of the P X variables, any of your predictors, we would use something called a partial F test. So we talked about F test here. this is when you try to testing linear association between y and the predictors. Basically, for predictors. Yes, and this is our hypothesis that we are testing. And when we really do the test, we will do a partial F-test. So, well, if you have, so this is always your, so this regular F-test that we have talked about here, this regular F-test is what you will do all the time as the first step if you want to test the association between y and any of the x predictors. If you have a significant F-test, then you might ask which of this p variable has a linear association of this y. Well, you can do p separate t-test with this null hypothesis being beta I equal to 0, but this has some interpretation issue if the variables are highly correlated. So instead, we will do a partial F-test to. So the null hypothesis for this partial F-test is that you set beta 1 to beta k being 0 and k less than p, and p being the total number of predictors in the full model. So where in the full model, all these betas are not 0 as our alternative hypothesis. So in the null hypothesis, we set some of them being 0. So that's why it's called like a partial F-test. We set part of those predictors coefficients being 0. So to get our test statistic, we need to define the corresponding residual sum square for the full model and the residual sum square for the reduced model. So this for the full model is right here, where you have beta 1 to beta p. All of them are non-zero. Where in the reduced model, this is the residual sum square for the smaller model, where you have only from beta k plus 1 to beta p being non-zero. So, and once we get those, we can define the partial F-test statistic by this. Like you find this residual sum square for reduced model and full model, and their corresponding degree of freedom. So remember, the degree of freedom is the total number of predictors, the total number parameters you are going to estimate in your model. Like for example, this reduced model would have p plus 1 minus k, where the full model have p plus 1 degree of freedom because we have from beta 0 to beta p. So that's p plus 1, right? And the reduced model, we set k of them being 0. So the rest would just be p plus 1 minus k. So then their difference will just be k, right? The difference of the degree of freedom for the reduced model and the full model will just be k. And the denominator for this partial F-test statistic is this residual sum square of the full model divided by its corresponding degree of freedom. So basically, it's this this F-test statistic. Well, now we talked about excuse me. We talked about F-test in general, like for a single model, and for a single model, like the full model, you have all p variable, and you want to test if this y have any association with this many parameters, with this many predictors. And we talked about all the terms in ANOVA and the difference of adjusted R-square and the original defined R-square. So when we're comparing model with different number of predictors, like full model and reduced model, they have apparently reduced model have less number of predictors, right? We would use adjusted R-square for comparison. And for testing, like if we want to test, like if this full model or the reduced model, which one is a better model for the data, we will use this partial F-test statistic. Now we will get to our example to illustrate this ANOVA and partial F-test. Okay, so again, we'll continue with this NYC restaurant dataset. And now we do, remember when we do this multiple linear regression, we see that service, this predictor service being not significant. So we will consider remove that for our partial model. And the full model, let's run this partial model with only 3 predictors, and our full model is this 3 predictor with some interaction term. So these are just some more terms comparing to this partial model, and we'll do comparison of these 2. Right, we did our partial model, and this is our full model, where we have two more predictors included. So this interaction term is nothing but this east variable times this food variable, and this east variable times the decoration variable. So if you call it x1, x2, x3, and then this is x1, x3 times x1 and x3 times x2. So full model has apparently more terms compared to the partial model. So if we do a summary, this one would give you, the partial model give you the estimates for this x1, x2, x3, the coefficients for x1, x2, x3. So that's beta 1 hat, beta 2, and beta 3. And this is our beta 0. And for the full model, you will see the corresponding estimate for these 2 extra terms. And this is for the interaction. We will mention a bit more about interaction terms when we talk about ANOVA next. But for here, we just compare, we just want to do a partial F-test for this to see which one is better, to see if we should include this 2 extra interaction term or not. Let's take a look at the so this is how you do an F-test. You just put the full model and partial model as the arguments. No matter which one goes first, this ANOVA function would identify which one is a smaller model and which one is a bigger model, which is the full model. So in this case, we have, so it will give you the residual sum square and the derivative is yeah, it's n minus 1, well, sorry. So this derivative is 2. Let me go back. The degree freedom for the reduced model should be plus p plus 1 minus k. Well, I think this derivative is not. Let me do ANOVA with a single model, which So if you do this, it will give you the ANOVA table. I mean, well, it's kind of a F-test for this full model. ANOVA table, sum square distribution. Well, I think this distribution are not except for this one. Like if you do C, you will know. Okay, so this is your total number of your data. So the residual, so this corresponding to should corresponding to the RSS degree freedom, which is n minus p and minus 1. So here we have, for the full model, we have 1, 2, 3, 4, 5 plus 1, so that's 6. So that's n minus 5 minus 1. So yeah, this one is giving you the residual sum square corresponding to degree freedom. But for this ANOVA, yeah, this residual sum square is right. Okay, yeah. So you should look at this degree freedom. So this is n minus 5 minus 1. So p equal to 5 in our case, in the full model, 1, 2, 3, 4, 5, p equal to 5. So n minus p minus 1 would be this, corresponding to the residual sum square, and the other is n minus p minus 1. Oops. Yeah, it's this thing. So that's 164. So the difference of these two is just this 2 term, right? The difference of these two is this k. K equal to 2 here, because we removed 2 terms in the reduced model. Yeah, so this is the, so I'll just leave it here, just in case you need it. Yeah, so this is how you do a partial F-test. You find it will provide you the degree freedom and the residual sum squares corresponding to the full model and the reduced model, and the F-test statistic as well as the p-value. So this test is performing for this partial F-test, where in our example that we have, I should say, like we have, in the full model, we have 5 parameters, we have 5 predictors, and in the partial, in the reduced model, we removed the beta 4 and beta 5. So basically in this case, we have H now being beta 4 and beta 5 being 0, right? So, okay. And we got our p value, which is greater than, if we are doing 95% level, like if our significance level being 0.05. So for this case, we would fail to reject. Yeah, so we fail to reject our null hypothesis. That means the reduced model is better. So the null hypothesis supports this reduced model, the smaller model. Okay, so this is how you do a partial F-test and find what your hypothesis testing is, what are the hypotheses you are testing, and how to get a p-value and make the decision according to the output. Let's just file this, and Yeah, I guess that's it for this example. So just in case you need this, I'll just comment it out. This is the function you should use for this partial F test.